Hello there. Till now we've seen the concepts on how images are formed in conventional TEM imaging, how diffraction patterns are obtained, and how you analyze diffraction patterns. In today's lecture, we will move into a very important concept on high resolution imaging in TEM. When I say high resolution, it just does not mean that I'm actually looking at atoms, but I'm actually looking at lattice fringes when I'm using the microscope operated under special conditions. Unlike the previous mechanisms of contrast where we were primarily focusing on amplitude contrast, high resolution imaging in TEM primarily focuses on phase contrast, which is a very important contrast mechanism in electron microscopy. In this lecture, most of the content you would see is actually what I've learned from reading the book from Professor Tanaka. It is Electron Nanoimaging, Basics of Imaging and Diffraction, and also drawn some inspiration from the classic text from Williams and Carter. And there is this beautiful paper from Professor Dirk van Dijk, which is published in Advances in Electron Physics. So with that, the first question that comes to mind is, when I'm trying to view something at a very high resolution, am I actually looking at the atomic columns or lattice fringes, or am I really looking at the atoms? So when I look at high resolution imaging in TEM, what you need to understand is the atomic columns that are there in your crystalline lattice all start acting as scattering centers. Let us look into a few details of this. So in optical microscopy, in general, the contrast arrives from absorption of light. You take any kind of a sample, let us say on a transparency, you would see that there is some contrast, that is when you are operating an optical microscope in transmission mode, or if you look at some kind of a metallurgical microscope, either by reflection of light, you get some sort of a contrast. Now, depending on the kind of features you are looking at, there are certain ways in which the angle of scattering changes, and then the contrast also varies. Now, when it comes to transmission electron microscope, do you actually have a similar interaction happening, is what we'll try to look at. So when the electron beam is being accelerated at very high voltages, that is around 200, 300 volts, or even in the older days when the electron microscope was accelerated at 1.3 million electron volts, the velocities of electrons are so high that you have sort of an elastic scattering phenomenon, and there is not a significant fraction of absorbed electrons. So this raises the question, if electrons are not absorbed or blocked, what produces the image contrast? In X-rays, we've seen something called as attenuation. What really is happening inside an electron microscope? So the answer is, like I was introducing on the previous slide, phase contrast. This is actually the phenomenon on how the scattered electrons interfere with the unscattered electrons, and then what changes happen and how do you produce some sort of an interference pattern is what we'll understand in high resolution imaging. So the entire imaging theory of high resolution electron microscopy builds on this particular principle, where you have some sort of a phase contrast. So if you consider how does a single atom behave when it encounters a fast moving electron, let us try to lay a few principles on this. So what is a single atom for an electron? When I say an electron, here is an electron which is propagating along the optic axis of the microscope. So if you see, you have something called as the electrostatic potential of an atom. When we initially introduced the Rutherford backscattering and we introduced the concepts of scattering cross section, we've seen that when there is a fast moving electron interacting with an isolated atom, this deviates its path at an angle of theta, and then we related the angle of deviation through the scattering cross section to the accelerating voltage and the atomic number of that particular atom. Now, based on this, we build the foundations of the mass thickness contrast. Now, the other way to look at this is, if your single atom is actually described as a three-dimensional electrostatic potential, What do I mean by this? The nucleus is positively charged. There's a negative electron cloud surrounding the nucleus. Now, because when the electron cloud is actually sort of shielding the nucleus, the potential that you see or the potential that the incoming electron sees with respect to the nucleus is sort of screened, and you can approximate it with what is called as the Coulomb or the Wenzel potential. So, what exactly is this Wenzel potential? You can see that the way when light propagates through a medium, there is some sort of change in the refractive index which can cause a deviation in the path of propagating light. Likewise, when a charged particle or an electron encounters an isolated charged atom or a column of atoms, the Coulombic potential of these atoms together can sort of modify the path of the electron beam. That is what we established from the scattering expression. But now if I view these atoms arranged in sort of a periodic fashion, you can come up with some kind of a potential. So what I mean by this is, the atom is no longer an obstacle, but it behaves like a potential well. So this potential well, you can always estimate what sort of a charge is associated with this and how the electrostatic potential is, and how this induces a phase shift. If I look at the wave equation of the electron that is propagating, I can always introduce a phase shift term into the wave vector, into the wave equation, and then start building the foundations of this. So if I look at two equivalent pictures of an electron atom interaction, we've been looking at the sort of particle picture of interaction based on which we saw the Rutherford scattering and the scattering cross sections and so on. But if you look at it, the electrons passing near the atom are deflected. There is a strong deviation in the path, and then in typical electron microscopes, for elastically scattered electrons, we said it is a deviation of somewhere between 0 to 20 milliradians, and inelastically scattered electrons scatter at larger angles. The atom, we assume, is scattering outward. Based on this, the scattering cross-section theories have been built, and once these atoms are scattering the electrons to deviate outward from the path of the electron beam, the objective lens again is refocusing them towards the backfocal plane. So what you should remember is that in this picture, we are assuming that the electrons are not absorbed. Out of the several interactions that happen when an electron beam is interacting with the specimen, there would certainly be a very small fraction of absorbed electrons, but largely we are assuming all the electrons are transmitted forward, and then there is a strong scattering event. The total intensity is actually conserved. So when I look at the wave picture now, what you should see is, when the electron passes through a potential well, or like the atom is now acting like a source which can scatter the charged electron wave, the speed can change slightly. This is analogous to what we've drawn comparison with the change in the speed of light propagating through a medium, and we have related it to the refractive index. And when this happens, this also induces a phase shift. So the atomic columns which are lying in a crystalline sample would tend to introduce a phase shift. And then if I draw the analogy with wave optics and look at light interaction with matter, we have the refractive index, which is of course a complex number. Similarly, in terms of the potential and the electrostatic potential of the atom, you can always write an equivalent to the local refractive index due to the presence of a column of atoms. So this can be defined as n of r or eta of r is having some expression of the form square root of E plus V over E, where Vr is the electrostatic potential of the atom and E is the accelerating voltage of the electron. Now, that is what I was just mentioning. So the atom now acts like a phase shifter, but not really an absorber. I think in one of my earlier lectures, I've introduced this concept already called as the electrostatic potential. We'll look at it once more. So if I want to understand the phase shift that is caused by an atom, let us look at this picture. If I have a single isolated atom, and let us say for an electron wave which is having a planar wave front is interacting with this atom through a depth of delta z here, the phase can be modified as, so the phase can be seen as some kind of a complex number, and due to the presence of the electrostatic potential as introduced earlier, the change in the phase of the electron wave as a consequence of the interaction with the atom can be written with introducing the electrostatic potential in the exponential term. So what is happening is, when the incoming electron with some kind of a wave vector as exponential 2 pi I kz is interacting with a single isolated atom, there is a phase shift introduced, and this also causes a deviation in the path. Now, as the electron travels through the distance delta z, which is approximated as the thickness of the single atomic layer here, the phase shift it is inducing can be accounted in terms of a value like this, and if you substitute this value for the refractive index, you get an expression over here which is eta is sigma times Vr over delta z. So this is your electrostatic potential, and here is your thickness term which is introduced here. So sigma is actually written as pi over lambda, which is your wavelength, and E is the energy at which the electron beam is propagating, and this leads to what is called as the exit wave function. So in principle, when I have an isolated atom, the deviation in the path that is caused can be written in terms of the 2 dimensions with some kind of an expression called as the exit wave function, which is having this form, where psi s x y is the scattered wave due to a periodic arrangement of atoms, and the exit wave can be visualized as some kind of a complex number where you have your electrostatic potential of the atom accounted for in the phase term. Now, based on these kind of concepts, something called as the phase object approximation has been introduced. So what does this mean is, essentially because of the electrostatic potential of the atom, you are assuming that when an electron beam is interacting with a specimen, you are introducing a phase shift. So for understanding any of these interactions that happen in electron microscopes, a concept called as the phase object approximation has been introduced. So what exactly is the phase object approximation? You have a very thin specimen, you have a very fast propagating electrons, high energy electrons, and the scattering is weak. This is what we established in our previous concepts as well. I wouldn't call it especially as a weak scattering, but the angles of deviation in a transmission electron microscope are known to be extremely small. So this is kind of termed as a weak scattering phenomenon. And the amplitude more or less remains unchanged. And as a consequence of this kind of an approximation, you can get the exit wave as psi s is exponential I sigma times Vp of x comma y, where this is my electrostatic potential. This is what we have seen here. The projected potential is the other term that we use for this. And if I now integrate this over the 3 dimensions, I can account for the projected potential that I have from the exit wave. But what is interesting to note here is, when I have a phase object approximation, the amplitude here, the amplitude component of this particular exponent has not changed, it remains unity, and there is only a variation in phase. This is kind of a hypothesis which is built to understand the fundamentals of the phase contrast mechanism in transmission electron microscopy, where you have something called as the phase object approximation, and the variation in intensity is coming only as a consequence of the variation in the phase. This is called as a pure phase object. In reality, this is not actually the case. So if you look at this, when I record an image, I am recording only the amplitude, and the pure phase object would not give you, from this kind of an expression, any amplitude variations. So you would see the amplitude as unity everywhere. So why a pure phase object gives no image contrast is the wave is transferred through an objective lens. We've seen the ray diagrams earlier when we understood how does the lens function. We understood that from the object plane to the back focal plane, you can look at the modulation as a Fourier transform, and from the object plane to the image plane again, you have an inverse Fourier transform. So at the image plane now, the wave function actually becomes something of this sort, which is psi I of xy is, I have a Fourier transform and an inverse Fourier transform which is equal to my projected potential, which is of this form. So the image intensity then is actually unity. If I take a modulus of this, it becomes unity. So according to this pure phase object approximation, you would have nothing visible when you have only the modification of the electron wave front just due to a phase shift. So this is a fundamental result. A perfect microscope cannot image a perfect phase object. Then how do we see something inside a transmission electron microscope? So to understand this, a concept called as a weak phase object approximation has been introduced. So what exactly is a weak phase object? So for single atoms, when the refractive index component is sigma times the projected potential, sigma times the electrostatic potential of the isolated atom, which is significantly less than 1. In the complex notation that I have written, if you take a linear expansion, you can ignore the exponential term. The exponential, which has the form I eta, can be expanded as 1 plus I eta. So this simplifies the calculations for single atoms and for very thin specimens. And if I look at the image intensity under the weak phase object approximation, the intensity now becomes something of this form. So when I've taken the linear expansion of the exponential term by ignoring the higher order terms, I have something of this form, and from here my intensity actually becomes somewhat like this. So even under the weak phase object approximation, the contrast actually becomes 0. It remains unity. If you look at this, here is what remains in the weak phase object approximation. But then the question that arises is, where does the contrast come in transmission electron microscope? So where does the contrast come from? Thankfully, because we are using electromagnetic lenses, if you remember in the very beginning, I've introduced the concept that your lens and your imaging system is acting as some kind of a wave modulator or a phase modulator, and it introduces some kind of a phase shift to the electron wave front. So thanks to the aberrations that are present, so the objective lens now introduces a phase shift that depends on the spatial frequency. So if I look at the schematic that is shown here, if I have a lens like this and then I am introducing some kind of a phase shift by changing the focus, you can see that the path of the electron wave that is propagated through the lens has a certain phase shift, and this the path difference here can be related in terms of the phase shift, and you can start modeling what actually happens or what kind of modulations the lens does. So if I look at the phase shift that is introduced, if I look at the path in front of the lens in a little more detail here, the additional path that is traveled, if it is represented in terms of some angle, the additional path is in terms of some angle epsilon here, the phase shift that is introduced. You can always model this, and for all these variations in the phase that are actually caused due to the lens, there is something called as the lens aberration function or the lens transfer function. So let me introduce this concept called as the lens transfer function here. So in terms of the spatial frequencies here, so if you remember, I mentioned that when I have an objective lens, so if I place an object at the object plane, what I collect at the back focal plane would all be in terms of the spatial frequencies. Now if I have a two-dimensional system here, if I look at the 2 dimensions of the back focal plane, I have the spatial frequencies as u and v, and the lens transfer function is written as some kind of a complex number which is e power I chi, where chi is actually the aberration phase function, which is written in terms of the spherical aberration introduced by the lens as well as the phase shift caused by the defocus. So as I was mentioning just a short while ago, because of the defocus as well, you have a phase shift which is introduced, and inherently, because the propagating electrons do not all converge at a single point, you also have another disk of confusion which is introduced, and there is something called as the spherical aberration. So here you can look at aberration as also introducing change in the velocity or again change in the phase of the electron beam that is propagating through the lens. So the aberration function, based on some of the ideas or concepts from optics, is given by an expression of this form. And now if I look at this, the CS is actually a spherical aberration, delta F is defocus, and the electron wavelength is lambda. So what you can look at this is, lens actually behaves like a spatial frequency dependent phase plate. So your lens is introducing phase shift, and because of all the aberrations that are existing, the planar wavefront which is incident through the lens, and remember in our construction of the electron microscope, what is going through the lens is actually the exit wave. So you already have the component of the electrostatic potential of the specimen inherently inducing a small phase shift, and in addition to that, you also have the phase shift which is introduced due to the aberrations of the lens, and collectively all these things together result in some kind of a contrast in high resolution imaging. And this idea of taking the lens transfer function as an exponential of the aberration phase function, which is also a complex number, introduces a term called as the contrast transfer function. So what exactly the contrast transfer function tells you is, when I have an object and it is propagating through a lens, an electromagnetic lens, when the electron wave that has interacted with my object is propagating through the electromagnetic lens, what then happens is, the phase shift that is induced is consisting of the components of the electrostatic potential, the thickness of the sample, the defocus, and the lens aberrations all together. So if I look at the contrast transfer function, the ideas of these have originated based on the initial theories from Otto Scherzer, where the aberration function, if you take the first differential of this with respect to the spatial frequency, you end up with an expression like this. And if I now try to understand at what point this expression becomes 0, I can get a value of defocus as some negative value of Cs times the square of wavelength and the spatial frequency. So what this tells us is, from the weak phase object approximation and the phase object approximation, you were assuming that initially that there is no variation in the intensity after the electron beam has interacted with the specimen, whereas because of the spherical aberration of the lens, you can actually introduce some kind of variation in the phase and the contrast, and eventually if I look at this particular aberration function as a complex number, and if I write this as exponential minus I chi u, if I take the expansion of this, it is cos chi u plus I sin chi u. This value actually gives me an estimate of what all these aberrations together result in. So this particular expression tells me that the complex component of the aberration function, which is the sin chi of u, gives me an idea of how all the aberrations together induce a phase shift, and when I plot this as a function of spatial frequency, I get something called as the contrast transfer function. So what actually this derivation from Scherzer gives us is, negative defocus can actually counteract the spherical aberration at certain spatial frequencies, and you actually get a good contrast in the image. So the concept of the contrast transfer function is the phase that is modulated as a consequence of multiple interactions that are happening considering the atoms as scattering centers. This is giving you the component of the projected potential in your scattered electron wave, and in addition to this, whatever aberrations are inducing a phase shift can all be measured in terms of something called as the contrast transfer function, which appears like this. So the contrast transfer function essentially helps you modulate the phase into an amplitude, and you can record this information. So if I look at this, this is of course analogous to the Zernicke phase contrast in optical microscopy. So if the lens phase shift equals pi over 2, you actually get a maxima, and that is what we see here. So if I look at the contrast transfer function for 3 different conditions, in an ideal scenario you would see the transfer function appearing like this, which is linear, but because of the aberrations, the expansion of sinusoidal of this particular term, when plotted against the spatial frequency, appears like this. In the under focus condition, you see this at -1, and at the point where this intersects the spatial frequency axis, this is called as the point resolution, and you would see that these phase shifts whichever are happening would actually go like a function which dampens out after a distance, and at the distance where this becomes more or less 0, so if I call this as an envelope function, this eventually dies out like this, and somewhere here this is called as the information limit. So when I do the same in over focus condition, my contrast transfer function starts appearing like this, and the idea of this contrast transfer function is not just a mathematical concept, but it actually gives you what exact phase shifts have happened as a consequence of the defocus or the spherical aberration, and how your amplitude of a high resolution image is produced. And if I look at this by using a sort of a weak phase object, and when I look at the ray diagram of when I place an object at the object plane, how the contrast transfer function can be visualized in a microscope is given on this particular slide. So let us say I have an amorphous carbon film here, which is having a very low scattering potential, and it is amorphous, so there is no consequence of the Bragg's diffraction that can give you some kind of a diffraction contrast in this particular case. What you see here is only certain variation in the thickness. Now, if this particular electron wave is going through the lens, I would obtain some kind of information at the back focal plane which can be related through the Fourier transform. So, if I look at the Fourier transform of the amorphous material at the back focal plane, so what I see is when I change the focus, I actually am varying the spatial frequencies here. I can actually visualize as a consequence of change in the focus how my contrast in the image here is changing, and likewise how the contrast transfer function is varying. And this looks very similar to the graph that I showed you earlier. So what you have to note here is when I look at the amplitude which is obtained from the Fourier transform here, I am actually getting the modulus of this particular value. So I see this appearing on the upper side of the scale on the graph, unlike the previous graphs earlier. So if I look at the snapshots of how the defocus has actually modified my contrast transfer function and has given me a change in the contrast, is at zero focus I do not see much difference between this randomly oriented amorphous area and the free space here. And if I look at the contrast transfer function at this particular case, it is appearing somewhat like this. And if I now induce a small defocus of approximately, I think this was minus 50 nanometers, I start visualizing the profile like this. And so if I look at a large defocus of approximately minus 300 nanometers, the contrast has significantly improved here, and my contrast transfer function starts appearing like this. So if I want to build on this and understand how my contrast from a high resolution image varies from a scenario from an isolated atom to a periodic arrangement, what I need to understand is with a single atom, the phase contrast that is induced can be written in terms of an expression like this. And the interpretation is the regions with positive projected potential appear darker. The single atom actually appears as a dark spot, and by changing the focus I can switch from a dark spot to the bright spot again, and the spot is actually broadened by the transfer function. The image is actually not true atomic size. There is something called as delocalization as well. I'll talk more about it when I start introducing lens aberrations at a later stage. So the image is actually not true atomic size, and when I have the case of two atoms or an array of atoms interfering, the exit wave from the crystalline sample producing an interference pattern, we have to understand with the simplest scenario where I have a two atom case first. So when two atoms are present, the exit waves actually, you can look at the propagating wave front by the principle of superposition of the waves, and if I have the superposition of the exit waves, the Fourier transforms also interfere, and the image contrast then depends on atomic separation, the spatial frequencies transferred by the lens, and also based on how the atoms are actually arranged. And you can connect this directly to the electron diffraction theory, where if I am looking at the object plane, I am looking at the real space, and when I am looking at the back focal plane, I am looking at the reciprocal space, and we introduce the reciprocal vectors also into understanding of the electron diffraction patterns. Likewise, if I look at the scenario where I have an isolated atom or a point which can actually cause a phase shift at the reciprocal space, I have a function which appears like this: g of x comma y is some g of r. But if I have two atoms now, the pattern that is produced here is a consequence of interference between these two waves, and this has a form which is like this. So it is the projected potential, and here it is the electrostatic potential, and this becomes my projected potential, and it can also be written as a convolution of these two quantities. So if I assume that there is one atom at one position and another atom at some other position xi and yi, so I can look at this as a convolution between the kind of the weak phase object approximation that we showed. So the projected potential with the lens aberrations together actually can give me an idea of how my projected potential can be determined, and in terms of the spatial frequency, this appears like this. So if I look at the scenario where I have two atoms actually interfering together to produce my exit wave, I can get an exit wave expression which appears somewhat of this form. Now before I understand this further, let me introduce you to another concept on how I should start visualizing my electron microscope as some kind of a phase modulator. And to introduce this, I would like to introduce a concept called as the point spread function, or even before the point spread function there is something called as the impulse response function. So what exactly do I mean by this impulse response function? Let us say I have an object like this, and if I am visualizing this with my naked eye, the details that I see are somewhat different from when I record an image like this. The image that you see is not certainly a one-to-one correspondence to the object that I see. So the recording medium, which is a camera that I use, introduces some kind of a modulation to the information of the object that I have. Likewise, in any imaging tools, you can start introducing some kind of a modulation, and typically, because in all microscopes we actually use circular apertures, a point object starts appearing like the airy disk that we have actually talked about when we introduced the concept of resolution. So likewise, within a microscope, a point object starts getting blurred and it appears more and more blurry, and this is called as the point spread function. So what I can now do is, if I want to look at transmission electron microscope as some kind of a mathematical modulator, if I look at this particular schematic, which is from the paper from Dirk van Dijk that I was mentioning in the very beginning, if I look at the incident beam, which has some kind of wave equation which is represented as f of x comma y, the projected potential from this, when it goes through the objective lens, can be visualized in terms of the Fourier transform at the back focal plane, and that is what we saw in terms of the contrast transfer function. And an inverse Fourier transform of this is what you record at the image plane. Now, the object function, which includes my electrostatic potentials, if it is represented as some phi of r, the modulation that is introduced, that is a subset of the impulse response function or the kind of point spread function of the microscope, gives you an image which is a convolution between the object function and the impulse response function. And as you can see, if my object is like this, and if my point spread function due to the imaging device is like this, The image I record now is a convolution between these two quantities, and it starts appearing like this. Now, here is what we also introduced in terms of the lens transfer function or the aberration function as well, and then the ideas of contrast transfer function were introduced. So, based on this, what you can see is by using the Fresnel approximation, I didn't go into the mathematical details of this. These are given in exceptional detail in one of the texts from Harald Rosa and also from Dirk van Dijk's paper. You can see that the projected potential is dependent on the electrostatic potential, the defocus that I actually introduce, and also on the aberrations of the lens. And essentially, this is what we are recording in a high resolution transmission electron micrograph. So, if I look at the concepts that we just saw in terms of schematics, imagine I were to visualize how atoms are arranged in a crystalline lattice based on our ideas from some kind of elementary crystallography. If we say that I want to simulate an image of a face-centered cubic structure, for example, now I did this thought experiment with help of ChatGPT. Let us say I want to get how the impulse response function of ChatGPT looks like when I want to visualize aluminum atoms projected along the 001 zone axis. I get some image like this. Now, the same thing, if I take two layers of aluminum atoms and if I build an image of this, and if we have a Manier overlay of layers, you should see some kind of a variation in the intensity like this, a simulated image of overlaid layers of aluminum to get a certain thickness. The intensity distribution that you see as a consequence of the phase modulation due to the electromagnetic lens might appear like this. Now, when I look at the same information in an uncorrected high resolution TEM micrograph, I see that what I think from the impulse response function from an algorithm versus some kind of a simulation in which I have introduced a few quantities can appear entirely different from an uncorrected high resolution TEM micrograph. So, with this, I think I have introduced a few concepts. Let me quickly summarize on what is important in understanding high resolution transmission electron microscopy. Firstly, your atoms are acting as scattering centers, and the images that I record in high resolution transmission electron microscopes are actually interference patterns. What I see here is a variation in the intensity as a consequence of phase shift caused by the columns of these atoms, which are also acting as scattering centers. And as a consequence of these atoms being associated with an electrostatic potential, we introduced a concept called as the potential well and the phase object. You see that there is some kind of a phase modulation happening. If I have an ideal phase object, you really do not see any kind of modulation and you cannot record any intensity variation. And then we had the weak phase object approximation, and then we also had the aberrations due to a lens which can be visualized as a complex number. And if I look at the imaginary part of this complex number, we have something called as the contrast transfer function. As a consequence of the errors that we have, as a consequence of the lens aberrations, you can induce a phase shift, and the phase shift can be visualized in terms of the contrast transfer function. And this contrast transfer function is dependent on the specimen thickness, it is dependent on the defocus, and we've seen how the contrast varies as the defocus values are changed. And finally, when you look at the uncorrected high resolution TEM micrographs, the images you see would actually be not exact positions of the atoms, but projections of these atomic columns, and these are more like lattice fringe images, but not really the exact positions of the atoms. In order to retrieve the exact position of atoms, you have to do something called as the through focus exit wave reconstruction. Now, before I move further, I'd like to end this lecture, and I'd like to take you to the demonstration sessions on the transmission electron microscope.